This video is about defining and also deriving the concept of voltage. In order to do so, we're going to look at the definition of potential energy of charges in an electric field. We're going to see how this is related to the work performed on charges when they move through a conductor inside such a field, and also what the role of the current, the electric current, and the material through which the charges flow play in all this. And by the end of this video, you will find a definition that already has great similarity with the well-known Ohm's law, which you surely have heard about. My name is Andreas from the Fearless Engineer, and here we go. Now, in order to get to our definition of voltage and also on the way derive it from some base equations, let's revisit what we have learned about voltage in the previous video, which gave us a broad overview on the concept of the voltage U. As we have seen, the voltage describes the ability of the electric field E to move charges over a certain distance. Here on the left hand side you can see a small diagram which contains a battery with a positive terminal and a negative terminal, and due to the charge difference between these two terminals we have an electric field which propagates through a wire, which is indicated by this blue arrow pointing from positive to negative terminal. And in this wire we have two charges right now in the example, one at this position here and one at the top position up here, and in between those charges there's a spatial difference, a distance L has been covered, and the voltage describes the loss of potential energy when the charge moves from the position closer to the positive terminal to the position closer to the negative terminal. Due to the fact that the technical current direction flows from positive to negative, we say that the positive terminal has the highest potential energy and the negative terminal has the lowest potential energy. And when we move an electron by the electric field from one position to the next, it gives away, it sheds a certain portion of its electric energy, comparable to the apple falling from a tree towards the Earth's surface, and the voltage drop is described by the product of the electric field and the length over which the electron has moved. And to understand why the voltage is defined as this product of path length and electric field, it helps to set up an energy balance to investigate the potential energy, which we will do on the next slide. On this slide here you can see this analogy between gravitational pull of the Earth on the left hand side and forces at play in the electrical field on the right hand side. We have already talked about what's happening inside the circuit caused by the electric field generated by the battery, and on the left side we can see an apple being pulled towards the surface of the Earth by its gravitational pull, and we can calculate the potential energy of an apple in a certain height h, which you might still remember from physics class in school as the product. The energy of this apple in this height is the product between mass of the apple and gravitational pull of the Earth and its height. So the higher we hang the apple, the higher will be its potential energy. The heavier we make the apple, the higher will be its potential energy. And this concept of potential energy in a gravitational field can also be transferred to the example of the charges within the electrical field of a circuit, and we can simply say that the mass of the apple is represented by the charge of the charges transported through the circuit. The gravitational pull of the Earth is represented by the electrical field generated by the battery, and the height of the apple is represented by the length over which we observe the motion of such an electron. So we have a very simple equation here which gives us the potential energy of a charge carrier depending on on the magnitude of its charge, on the electric field generated by the battery, and the length over which we observe the motion, for example, from the positive to the negative side of the terminal. And the negative side corresponds to the surface of the Earth, obviously. Now what we can do now, we can say that each point in an electric field is associated with a certain level of potential energy. So the apple hanging at 4 meters has a higher potential energy as the apple at 2 meters. The charge carrier which just has left the positive terminal of the battery has a higher potential energy than the one just arriving at the negative terminal. It has a potential. And if, for example, an electron in the field changes its position from a higher to a lower potential, then part of this potential energy, because energy is never lost but only transformed, is converted into kinetic energy. So by exploiting this potential difference between the terminals of, let's say, a battery, we can convert this potential energy into kinetic energy. And kinetic energy of electrons is our transport mechanism for energy into a circuit. And this change in energy between two positions in a conductor, this is called the potential difference. And potential difference is also referred to as voltage. So we have the potential energy of a charge carrier at a position 2. We have another position 1. And also at this position, we have a different potential energy. And if we subtract the two, what we get is this expression here. So if you recall the expression for the potential energy from the previous slide, Q times E times L, we can simply say that if we have a charge Q inside a field E and we move it from position 1 to position 2, this is what we get as a resulting equation. And we can simply substitute here L2 minus L1 by delta L. This is the difference, the length over which an electron moves in a circuit. And this product of E and delta L, this is what we call voltage. Independent of charge, it's only depending on the electric field and the length over which charges are moving. And in order to get to the energy definition, the potential energy, we have to take into account the mass of the apple, so to speak. And in this case, it's the electric charge of the charge carrier we are investigating. And now that we know what voltage actually is, let's look at the unit of voltage, which is the volt, obviously, abbreviated by the letter V. And it's named after the Italian physicist Alessandro Volta, who lived at the same time as many of his famous peers. For example, Ampere also lived in this time. And Volta laid one of many foundations of electricity. And in the module on the Coulomb force, we have already seen that the electric field E and the force, the Coulomb force Fc, are very closely connected by this simple relationship here. So the electric field E is simply the ratio between Coulomb force and amount of charge. And therefore we can express the voltage in this fashion here. So the unit behind voltage is nothing more than newtons multiplied by meters, which is the Coulomb force, multiplied by the length over which the charges are moving. So Newton meters divided by current times time. So current is represented by the amps and time obviously is the second. And this one here is simply the amount of charge. So these base units are also a way to express voltage in addition to volt, which is the commonly used unit, which we find in the literature in most cases. And based on this definition, we can say that the volt expresses the amount of work per charge that can be performed by a source. So volt describes an amount of work we can do normalized on the amount of charge, independent of the charge we want to perform the work on. And using the relationship between voltage and electrical field and also length over which charges move, we can simply replace the electric field in this equation which we have developed before in the module on the electric current, which is given by this relationship here, the current on the left side, the electric field on the right side, and material parameters in between. If it's not clear to you where this comes from, you might want to re-watch this video, and it's very interesting to see how we get to this equation here. And we can now take our new relationship which relates the voltage on the left side and these two parameters on the right side and substitute it into the electric field and then arrive at this definition here, which collects all the material parameters and then gives us a relationship between current and voltage and also the material through which the charges move in this gray box here. So we can say that there's a material-dependent relationship between current, which is the quantity of moving charges, and the voltage, which is the driving force behind these charges. And based on this relationship, it's very clear how we can get to Ohm's law, the famous Ohm's law. In the next step, we already have a relationship between current and voltage and some collection of material-related parameters, and we can easily see how these material-related parameters influence the resistance of the material, which is something which we will investigate in one of the videos to come. For now, that's all. If you have any questions, don't hesitate to drop me a comment down below. And also, if you like this video, leave a thumbs up and think about subscribing to my channel. And I wish you a nice day now. See you next time here on The Fearless Engineer.